Hello everyone. In our previous lecture, we have discussed the velocity triangle and we have seen that how to plot inlet triangle as well as outlet triangle, and we have also seen the importance of the velocity triangle. Okay, we can say the velocity triangle is essential tool to analyze the turbine performance. Okay, based on the velocity triangle, we are going to derive some of the equations that might be helpful to analyze the turbine performance. Okay, so in this lecture, I would like to discuss the analysis of impulse turbine using the velocity triangle. So let's begin our today's session. Okay, if you recall my last lecture, in last lecture we have seen that the inlet triangle and outlet triangle look like this. Okay, and ultimately it is the vectorial representation of different velocity of steam whenever it is passing through the turbine blade. For example, in this triangle you can say C1 stands for the velocity of steam whenever it is leaving the nozzle. Okay, CBL stands for the velocity of blade whenever steam strike on the blade, because we know that whenever the steam is getting passed over the turbine blade, at that time because of the momentum change, steam will exert a force on the turbine blade and blade will try to move in horizontal direction. So here we have a velocity of blade CBL and we need to plot one vector correspond to the velocity, and that is CBL here. Okay, so CBL stand for the velocity of blade in meter per second, C1 stand for the velocity of steam. Okay, now we have CR1. CR1 stand for the relative velocity of steam whenever it is passing over the turbine blade, because whenever steam is getting in contact with the turbine blade, at that time turbine blade has its own velocity while steam has its own velocity. So that whenever steam is getting in contact, at that time the effective velocity is relative velocity, that is CR1, but for simplicity you can say it is a resultant velocity. Then after, the horizontal component of C1 is known as the wall component of velocity, which is generated because of creation of turbulence here, because here turbine blade having a curvature path. So whenever the steam is getting passed over the turbine blade, at that time there will be a creation of some sort of the turbulency, and because of this turbulency, okay, we need to plot one vector. That vector is wall component. Okay, and wall component is ultimately the horizontal component of C1. Then after, as the flow proceed across the turbine blade, it will flow vertically downward direction, so that the vertical component of C1 is known as flow component and designated by CF1. Okay, so it is all about the inlet triangle. Okay, simple recapitulation. Okay, and here I forgot one thing to tell you, that the angle that made by C1 is alpha 1, which is nothing but nozzle angle, and the angle made by CR1 is blade angle, because whatever the shape of blade, it must be followed by the steam whenever it is passing over the blade. Okay, so blade angle must be followed by the relative velocity. So here we have theta is blade angle at inlet. Okay, so it is all about the inlet triangle. Now similar way, for outlet triangle we have one common vector, that is CBL. Okay, steam is leaving with velocity CO, CRO is our resultant vector, then after CFO is our vertical component of C0 or O you can say, then after horizontal component of CO is CWO. So it is all about the velocity triangle. Now we know that according to the Newton's second law, the force is proportional to the rate of change of momentum. Okay, now what do you mean by momentum? Momentum is nothing but mass multiplied by change of velocity, and in this case particularly force is equal to, you can say, mass flow rate of steam multiply by change of velocity. Okay, so based on the triangle, now we are going to derive the equation for the force and work done. So here we have combined triangle, okay, that we have discussed in our previous lecture. It's just recapitulation, okay, but keep this triangle in your mind, because in our next presentation we are going to use this triangle as our base. Okay, again we have discussed this thing. Now force, you can say force is proportional to rate of change of momentum, and mathematically you can write force is equal to mass multiplied by acceleration. Okay, acceleration is nothing but change of velocity. Okay, or you can say it is, this equation indicate ultimately momentum. Force is proportional to rate of change of momentum, so mass multiplied by change of velocity will give us the force. Now you notice one thing in previous slide, that whenever the steam is getting passed over the turbine blade, at that time turbine blade is tried to move in horizontal direction. So here we need to find the horizontal force. So horizontal force is nothing but mass flow rate of steam multiplied by change of velocity. Here you can say we have a mass flow rate of steam is m dot s, okay, multiplied by change of velocity. Okay, steam will flow over the turbine blade and exert a force because of which component of velocity? You can say whirl component of velocity. Whirl component of velocity is one of the main component because of which the steam will exert a force on the blade. So here change of velocity is nothing but the difference of whirl component of velocity at inlet and outlet. At inlet we have whirl component of velocity Cw1, and at outlet we have whirl component of Cwo. Okay, so Cw1 minus Cwo is equal to change of velocity. But notice one thing carefully, that the inlet component of velocity, I mean to say whirl component, is in right hand direction, toward right hand side, I mean to say, while the outlet whirl component is toward the left hand side. Okay, inlet component of velocity is toward to right hand side, while the outlet component is toward the left hand side. So we are dealing with velocity vector. So one is right hand side, one another is left hand side. So we need to put the negative sign. So Cw1 minus Cwo. So minus is getting positive. Okay, so final equation of force exerted by the steam on the turbine blade is equal to ms multiplied by Cw1 plus Cwo. So it is all about the force. Okay, clear to all? Now second, I would like to brief you about the work done per second. Now before going toward the work done per second, just tell me, what do you mean by work done? You can say the work done is product of force multiplied by displacement. Now what about work done per second? Work done per second is nothing but you can say the force multiplied by displacement divided by time. Displacement by time is nothing but the velocity. So work done per second is nothing but force multiplied by velocity. Force multiplied by velocity. Okay, here you can see force multiplied by velocity. Okay, so here we have force with us, that is m dot s multiplied by Cw1 plus Cwo multiplied by velocity. And here we have to consider the velocity of blade, because we are producing work on the blade and we will obtain work from the turbine. Okay, by using steam we are producing work on the turbine blade, so we need to consider the blade velocity, that is Cbl. So work done on blade, okay, is equal to m dot s multiplied by into bracket Cw1 plus Cwo multiplied by Cbl. So it is all about the work done. Now I would like to brief you about the blade efficiency. What do you mean by efficiency? Efficiency, you can say output by input. As the output we obtain work done, and as the input we are supplying kinetic energy of steam, because steam is coming from the nozzle, so it will create the jet. Okay, so as the input we are supplying kinetic energy. So kinetic energy is 1 of mc1 square divided by 1 half mc1 square. Okay, simple. So we have work done equation with us, that is ms cw1 plus cwo multiplied by cbl, now divided by kinetic energy. Kinetic energy is 1 half mass flow rate of steam, that is ms, multiplied by velocity of steam at inlet, that is c1 square. Okay, so this equation represent the blade velocity. Okay, now we have to find next thing, that is the stage efficiency. So what do you mean by stage efficiency? You can say stage efficiency is the ratio of work done on the blade per kg of steam flow rate divided by total energy supplied per kg of steam. Okay, so per kg of work done means we have to assume mass flow rate of steam is equal to be 1. So work done is equal to be CBL multiplied by CW1 plus CW0 or CWO you can say, divided by energy supplied per kg of steam flow, that is nothing but enthalpy difference, okay, across the turbine blade, which is nothing but H2 minus H1 minus H2. Okay, so this equation indicate the stage efficiency. Okay, now next thing I would like to brief you is the axial force generated because of steam flow. Okay, so axial force is nothing but mass multiplied by change of velocity, as I told you, mass flow rate multiplied by change of velocity. So we have mass flow rate of steam is m dot s multiplied by the axial component of velocity, that is nothing but Cf1 and Cf0. So difference of Cf1 minus Cf0 multiplied by mass flow rate of steam will give us the axial force on the turbine, or you can say axial force on the wheel. Okay, so in our today's session we have discussed the force exerted by steam on the blade, then after we have discussed the work done formula, then after stage efficiency, okay, and finally we have discussed the axial force on the wheel. So it is all about the today's lecture. Stay tuned for the next session. Okay, thanks.